Gravity and Gravitational Waves, featuring Renee Leon, Dylan McCoy, Ryan Shin, and Zayed Truman, is an interesting topic on Earth and outer space. Imagine dropping a marble into a pond that to the naked eye seems to have no ripples. The effect once the marble hits the water is the creation of ripples. At the instantaneous moment, when the marble is hitting the water but has not yet broken the surface of the water, is what a black hole or some sort of object with mass in space would create as it is bending the space around it. Now let's say that we have two of these marbles, or for our purposes, two black holes or quasars, with an immense amount of mass close enough where their gravitational pull is so strong that they begin to pull each other as they orbit around the center of their orbital path. Eventually, the two giants will come close enough to each other that their bending of space-time will begin to merge together as they get closer to the center. Gravitational waves are produced during this process.
First, we should explain gravity. Sure, likely all of you know that the acceleration due to gravity on Earth's surface is 9.8 meters per second squared. You probably also know that everything in the universe that has mass is attracted to everything else in the universe with mass. So that attractive person in your second period is technically attracted to you as well. Congratulations. More importantly than your floundering love life is the fact that gravity holds all of the universe's marvels together. Whether it's a small world such as Earth's moon or the largest black hole ever found, S50014+81, gravity is their creator. In Newtonian terms, gravity is a force, with its own set of forcey rules. However, once Einstein came along and completely revolutionized our view of the universe, we began to realize that it's so much more than that. Gravity is a literal bending of space-time. Yeah, I know, just like those sci-fi books and movies like A Wrinkle in Time or Star Trek. But I digress. It's the action of a mass, usually referring to a planet, star, black hole, etc., compressing space around it. The best way to think about it is as a large funnel, kind of like the ones at the mall with coins that you throw in. They curve around the center and orbit it until finally dropping into the dark chasm below, where they can be picked up by an employee who's probably dead inside by now. On that happy note, it's time for a segue into black holes. Black holes are neither black nor holes, at least in the traditional sense. They come from a massive object, like a star, that's collapsed in on itself. The gravity of the situation, pun intended, is so large because the star's incredible mass is partially expelled and partially collected into the size of Rhode Island. Just to clarify, half a star just collapsed down to the size of the puniest state. This has a gravitational pull so strong its escape velocity, or the speed you need to reach to leave its gravity, is past the speed of light. This is why it's neither black nor whole. It's black because of the absence of light. Literally no light reflects off the surface of a black hole, since it isn't fast enough to escape its gravitational pull. So really, calling it an invisible hole would be more appropriate. Also, remember that black holes have mass. They're former stars, some of the most massive objects in the universe. Because of this, you have to understand that calling it a hole just doesn't work. Holes are empty. Black holes don't rip space-time as far as we know. They just absorb more mass into their own substance. Anyway, back to gravity. Like I said before, a black hole's gravity is so strong that it can hold light in its grasp. And the gravity of planets, stars, black holes, etc. warp space-time. So, given these two facts, it's pretty easy to make the jump to the fact that black holes warp space a lot more than a star or planet. Anything could hypothetically make gravitational waves, since everything with mass can warp space-time. However, black holes are going to be the focus of this presentation since they are friggin' awesome and also very large.
Like we said before, gravitational waves resemble the ripples of a pond, except, well, in the fabric that makes up the universe itself, and in higher dimensional planes. But still, they're similar. If the waves in a pool of water are formed from a rotating source, such as the propeller on a boat, they propagate outward in a spiraling fashion. This is the same as gravitational waves. The two are alike in their ability to carry angular and linear momentum and kinetic or gravitational potential energy away from the source. The waves act very similarly to dampened waves, with the tail end of the wave having a much longer wavelength than the source end. The rotating source that is producing the wave is a binary system of black holes. The two eventually combine into one larger death ball, and right at the end of their journey, the two black holes cause a large kick with an amplitude that can be as large as 4,000 kilometers of expanded space. This moment marks two events. One, the end of the production of the waves, and two, that the new combined black hole is displaced, possibly ejected from the host galaxy entirely.
Hey, guess what? It's time for another segue. This time, we're moving on to the history of gravitational waves and the methods of detecting their existence and potential uses. In 1905, a dude called Henry Poincare first came up with the idea of there being a gravitational equivalent to electromagnetic waves. It's not that hard to see why he thought this up, given similarities between their formulas and forces. Einstein was somewhat inspired by his idea to research and calculate this further. He ultimately found three types: longitudinal, transverse, and transverse. Everyone, Einstein included, dismissed these findings as a tad
Redonkulous.
In the 70s, though, the first evidence of gravitational waves was found. In 74, the first binary pulsar was found. For your information, pulsars are a type of black hole. This was the same time period that the electromagnetic interferometer was invented. This is a device that detects long wavelength gravitational waves. The LIGO, or Laser Interferometer Gravitational Wave Observatory, study began soon after, which was an effort to locate gravitational waves. It began searching in 2002. It was upgraded in 2004, and the binary black hole problem was solved by several people simultaneously in 2005. In 2015, the advanced LIGO begins operation. This confirmed the existence of gravitational waves.
Gravitational waves always pass the Earth. That's how LIGO was able to detect them. The strongest have a minuscule effect since their sources are vast distances away. The best and close example of this is the waves given off by the cataclysmic combination of the black hole system GW150914 reached Earth after a billion-year and light-year journey through the cold expanse of space. It arrived as a ripple in space-time that changed the length of a 4-kilometer LIGO arm by 1/10,000th of the width of a proton. To put that in perspective, that is 1.7 times 10 to the negative 15 meters. Still not in perspective, if you touch a table that would displace thousands of times more matter than was displaced in the gravitational wave, how that machine managed to detect a change that small is beyond us, but it did. This is like changing the position of Alpha Centauri relative to the solar system by the width of a hair. That's insane. Only the most cutting-edge detectors even have a chance to detect a change that small.
One of the oh so many formulas is the same as the formula studied in this class for sound waves, V equals F lambda, except in this case it is C equals F lambda, since the gravitational waves propagate at the speed of light. This may be due to the hypothetical boson known as the graviton. The graviton is a theoretical particle that carries the information of gravity. In the same way that photons carry the information of electromagnetism, and Higgs particles carry the information of mass. Gravitons, if they exist, would move at the speed of light, since all particles with no mass move at the speed of limit of the universe. However, due to the highly theoretical nature of the graviton, it's impossible to say if that elusive little particle is the substance, for lack of a better term, of gravitational waves.
Before we go, there are multiple potential uses for gravitational waves from a physics perspective. For example, physicists have detected gravitational waves affecting the cosmic microwave background radiation, which can help learn more about the early universe. Gravitational waves also affect the distance and therefore time of light from pulsars all the way across the galaxy. They can be used to measure the star's distance from the Earth. There's a lot of complicated and frustrating astro and quantum physics that goes into this stuff that takes a room full of smart guys and big computers the better part of an afternoon to calculate. This means that 4 high schoolers with laptops can't explain all the math in a timely manner.